La sesión. Hola, ahora sí. Muy buenas tardes a todos. Sean bienvenidos a esta conferencia, A Journey to the Exotic World of Nanostructures. Mi nombre es Patricio Rodríguez y en nombre del Tecnológico de Monterrey y de la Escuela de Ingeniería y Ciencias le damos la más cordial bienvenida. En esta sesión tendremos la participación del Dr. Monterrey, que nos hablará inicialmente de la forma de comprender la física general detrás de la dependencia del tamaño de las propiedades de los materiales y exploraremos algunas características interesantes de las nanoestructuras basadas en carbono. Discutirá sobre algunas características generales de los puntos cuánticos de grafeno, puntos cuánticos de carbono, y nos centraremos en los puntos de carbono amorfo, quien ha recibido mucho menos atención en comparación con sus homólogos cristalinos, más a palabras del Dr. Rey, glamorosos. Posteriormente tendremos una sesión de preguntas y respuestas con el fin de aclarar cualquier inquietud o duda que pueda surgir de este tema. Les recordamos que esta conferencia será en el idioma inglés, so I will now switch language. We appreciate your attendance and we are very happy that in these times which we live in a virtual world, you gave us the space in your agenda, which we know it will be of your interest. In this session, we have the participation of directors and professors of the School of Engineering and Sciences of Tecnológico de Monterrey, and we will show you the opportunities of research studies within the Tech Monterrey through the Tech Scholarship that it is awarded to talented students who seek academic, professional, and personal excellence. To begin the session, we will have the participation of Dr. Monterrey, who will present the conference, A Journey to the Exotic World of Nanostructures. Dr. Monterrey did his graduation and post-graduation in physics from the University of Calcutta in India. After a brief period of physics teacher in South Point High School in India, he proceeded to obtain a second postgraduate degree of University of Nottingham in UK in 2003. As a British Chevening Scholar, thereafter, he did his doctoral research in the area of silicon nanostructures and their applications from Bengali Engineering and Science University in Shimpur, India. His primary research interest is on experimental and theoretical investigations on semiconductor and hybrid nanostructures, with focus on understanding their size-dependent optical and transport properties. Prior to joining Tec de Monterrey as a professor in the School of Engineering and Science, he served in the Indian Institute for Engineering, Science and Technology in Shimpur as a faculty member for 16 years. He's now supervised 3 PhD and 36 postgraduate theses and is currently supervising far more PhD scholars. So without further ado, I leave this stage to Dr. Ray. Welcome, Doctor.
Thank you so much, Patricio. Thanks a ton. So, shall we begin? I mean, it's all set.
It's
Excellent.
all set. You can start.
Excellent.
I think you can. Yes, you have the screen, so you can.
Yeah. Good. So, welcome you all to this today's seminar, to this session, and I intend to present a short talk on what is nano. What is so exciting about nano? So as you already know that I am Mollard Ray. I'm new to this institute in this beautiful surrounding of tech with even more beautiful people around. The last 2 years that I have spent, nearly 2 years, not 2 years till now, have been a memorable journey for me. My office is somewhere here in Torre Sur of CTech. But incidentally, the day I got my office, from the next day, there was a lockdown. But this excellent campus in tech, as I said, with excellent people around, has provided the correct ambience, the warmth that is radiated everywhere has kept me going. And I'm really, really fortunate, and I feel lucky that I'm here. And I'm happy that I'm able to present to you today and take you through a journey to the nano world. Okay. Now, I guess all of you here are about to begin either your master's or your graduate studies in nanotechnology. So at the very outset, it is important to get an introduction to this amazing world of nano. So I start with the most obvious question. What is nano? Well, of course, all of you know what is nano. But this buzzword about nano, the excitement with the word nanotechnology is new. It started around late 1980s, early 1990s. The word nanoscience, nanotechnology didn't exist before the 1970s. But several decades before that, Richard Feynman, who was a legendary teacher and a physicist, a Nobel laureate, kind of gave a clarion call in one of his talks, where he said that there's plenty of room at the bottom, and everyone knows about that. And many considers that that probably was the beginning of the journey to the nano world. But as we know today, that nano as such is just a scale. The word nano comes from the Greek word, which essentially means dwarf, something small. And nano means 10 to the minus 9. I'm sure all of you know it. So just as we have milli, which is 10 to the minus 3, micro, which is 10 to the minus 6, nano, 10 to the minus 9, pico, 10 to the minus 12, femto, 10 to the minus 15, so on and so forth. The smaller scales. Just as we have the larger scales like kilo, mega, giga, tera, all of you are aware, particularly with respect to the memory sizes, which are increasing now. So nano, in that sense, is just another scale, which is 10 to the minus 9. So a natural question which should come to our mind is, what is so special about this nanoscale? We have something called nanotechnology. And of course, the technology that exists today is microtechnology. But why don't we talk about pico? Is it that if we go smaller and smaller, it becomes more and more exotic? That's the first question that we would like to ask. But before that, let me tell you that since nano is just a scale, we can attach the word nano not only to a length scale, but also to a time scale or a weight or a mass scale. We can talk of nanograms, we can talk of nanoseconds, so on and so forth. But here in nanotechnology, in nanoscience, we restrict ourselves primarily to a length scale, that is a nanometer, which is nothing but 10 to the power minus 9 meters. So what's there in nanoscale? In order to understand that, I would pick up from the world of materials. We all know that there are plenty of materials all around us, starting from something like as boring but as important as coal to something maybe as exciting as gold or diamond, or something which we regularly use like arroz, rice, buildings, everything they are made of materials. And these materials, they have certain properties. As scientists and engineers, we can classify the properties either as mechanical properties, electrical properties, magnetic properties, optical properties, thermal properties, so on and so forth. For example, we know that coal is black in color, it's solid at room temperature. So is gold, which has a golden luster. But we have other materials, for example, water, which is liquid at room temperature. It has a boiling point, it has a freezing point. And most of these materials, not all, but some of these materials, they are made of crystals. You know, there are two types of materials, crystalline and amorphous. In crystals, a typical crystal size of a single crystal is of the order of 10 to the power minus 6 meters, that's micron. A typical crystal in gold would be a micron or few microns, right? But in amorphous structures, we don't have crystals. But we know whether it's amorphous or crystalline, every material, finally, they're made up of atoms. And in atoms, we have a nucleus with electrons revolving around the nucleus. I'm sure all of you are aware of this picture. And if I look at a typical nucleus, atomic nucleus, the size of the atomic nucleus is of the order of femtometer. So nuclear scientists have been dealing with sizes which is of the order of 10 to the power minus 15 or minus 14 meters. The size of an atom, whether it's hydrogen or uranium, is of the order of angstroms, that is 10 to the minus 10 meters. Right? So where does nano come in here? Nano comes in exactly in between an atom and a bulk crystal, where you have some countable number of atoms. In a crystal, the number of atoms are very large, billions, tens of billions, thousands of billions, so on and so forth. But if you have something which is not very large, where the number of atoms may range from thousands to millions, that makes a nanostructure. So what is so special about it? Let's try to think. You see, when we have a bulk material, let's say gold or silver or water, they have some bulk properties. For example, we can talk about their melting point, their freezing point, their Young's modulus, their refractive index, magnetic permeability, electrical susceptibility. All these are properties, right? I can give you a piece of iron and a piece of silver, and you can immediately say that silver has a larger conductivity than iron. But you will never ask me whether this silver is 1 kilometer long or 1 centimeter long. It doesn't matter. It's a good conductor. It has a conductivity value at a given temperature. It doesn't matter whether that silver wire is 1 kilometer long or 1 centimeter long. But if I look at a silver atom and ask the same question, that what is the conductivity? Does it make any sense? The answer is no. Because a single atom, the term conductivity doesn't have any meaning. Similarly, we know that water is a liquid, ice is the solid form of water. But if I consider one molecule of water, is it solid? Is it liquid? Is it gas? That's a stupid way of addressing a question, because a molecule is a molecule. You can only conceive of a state, solid, liquid, gas, when you have a large number of molecules coming together and forming a bulk. So while I can talk of a melting point of ice or melting point of some solid, in case of atom, melting point, boiling point, Young's modulus, refractive index, all these bulk properties become meaningless. If not all, most of these bulk properties become meaningless. Right? So there must be somewhere in between when you start collecting atoms, putting them together to make a bulk. And you know, when it becomes a bulk, it doesn't matter whether you have a little bit of coal, whether you have a large amount of coal, whether you have a small bucket of water or a large, pond full of water, the boiling point is 100 degrees, more or less under normal circumstances. The freezing point is 0 degrees Celsius. But when you land up with one molecule, no sense. So somewhere in between, you expect that these bulk properties, which are present in a large collection of atoms and molecules, they start to behave crazily. They start to lose their significance. And that world, that regime, is the nano world, where material properties start behaving strangely. In the bulk form, most of the material properties are not dependent on the size or shape. In the atomic form, most of the material properties are meaningless. But there is somewhere in between the bulk and the atomic form where you have the nano world, where material properties behave strangely with regards to the size. So they have properties intermediate to that of bulk and atoms. Okay. Another key aspect of materials reduced to the nanoscale is that the surface area to volume ratio becomes very, very high, it shoots up. We can understand from a simple example. Say if I look at this cube of side A, the surface area is 6a square and the volume is a cube. Now, if I cut it into 8 equal cubes, the volume remains the same, of course, but the surface area, now you have introduced more surfaces, is 12 times a square. You cut it more, volume remains same, surface area goes on increasing. So the same volume, if you cut it, if you break it, you are introducing more and more surfaces, so the surface area to volume ratio goes up. That's one way of looking at it. Another way of looking at the same thing is you start shrinking the size of a material. What will happen to the surface area to volume ratio? See, area is like length square and volume is length cube. In case of sphere, it's 4 pi r square and 4/3 pi r cube. So surface area to volume ratio is always 1 over L. So as you make L smaller and smaller, the surface area to volume ratio increases as 1 over L. Right? There is yet another aspect of looking at it. When you are making a thing small, then the number of atoms which comprise that material, if I divide it into two parts, atoms on the surface and atoms residing inside. So the number of atoms on the surface at certain stage, when it's small, may become comparable to the number of atoms inside. In a usual bulk material, the number of atoms inside is much, much, much more than the number of atoms on the surface. But when you have something which is in the nanoscale, the number of atoms residing on the surface is comparable to the number of atoms inside the core. So under this condition, the surface plays a dominant role in determining the properties. And more surface means more interaction. So tiny nanoparticles, which have countable number of atoms, say thousands to millions or hundreds of millions, or even billions, they have a very large surface area, something like our coronavirus, which is very small and has a very large surface area, even more because of these spikes. Okay. So we have learned two key aspects. One is that nanoscale is intermediate bulk and atom, where you have countable number of atoms in that structure, which is called a nanostructure. And they have properties intermediate to bulk and atoms. And second, at nanoscale, the surface area plays a very important role because the surface area to volume ratio increases dramatically. Now, at this size regime, in the nano regime, material properties which are otherwise independent of size, amazingly, they start showing size dependence. For example, we know gold, right? And gold is so attractive, it's like the color is called golden. It has this typical color. We don't expect that if I take a piece of gold and I break it, will the color change? Of course not. If I make a plate of gold or a wire of gold, the color remains same. That is expected. You will tell me, what crazy things are you talking about? But when you reduce this gold to tiny particles, and if they can form colloids in water, then you will see that depending on the size of these gold particles, which are nanoparticles, they have different colors, starting from something like wine red to blue. Amazing. Copper. Copper is conductive. We know that. Doesn't matter whether I take a wire of copper or a ball of copper or a sheet of copper, whether I break it, it is conducting, it has a conductivity value, which is not dependent on size. But if you reduce these copper particles, the crystal size of the coppers, arbitrarily small to the nanoscale, then you'll see some strange things happening. First, their colors will change. And when they're very small, they become completely non-conducting. silicon, which is the mainstay of modern electronic industry. If you reduce it to the nanoscale, the silicon can emit brilliant lights. And this is nanotechnology, which is tuning properties by tailoring size, or if you may prefer to call it, tailoring properties by tuning size. So basically, you play around with the size of the particles, of the crystals, or of the clusters, and you get different properties of a material, which is impossible in the bulk form. Now, let me tell you that nanotechnology is nothing new. The word nanotechnology is new, but it's like old wine in a new bottle. The picture that you see in the screen right now is that of a Leesser Gus cup. This cup is in the British Museum in London. It's a very famous cup because of its brilliant colors. If you look at this cup from reflected light, then it appears green. But if you put a light source inside and you look at the transmitted light, then it appears red. This cup was made by the Romans in the 4th century AD. And until recently, no one knew why this cup had this strange behavior. But today we know that this cup is actually made of gold and gold and silver nanoparticles, which give this amazing texture and color to this Leesser Gus cup. But it was made in the 4th century AD. So the Romans definitely knew how to make nanoparticles, but they did not know what was happening. They knew the phenomena. They knew it phenomenologically, right? Now, of course, this is one of the examples, but we find many, many examples all around the world. I'm from India, so I take an example from India. There's a particular kind of steel which we find in some of the ancient structures in India dating back to the 6th century BC, which is wood steel. And it was only recently, in 2006, a group of researchers found that this kind of steel, they have some amazing strength and sharpness. It is because of encapsulated iron carbide nanowires in them. So the technology, at least a part of it, was known. But of course, the artisans of that point of time did not know what was happening, why this was happening. This is something what we know today. Closer home, the intoxicating Maya blue, azure. This blue, which is, drawn in Vedas, which was widely used by the Mayan civilization people from the 8th to the 16th century. And again, in 1996, a paper was published in Science which said that this amazing color is because of something called a superlattice of metal and metal oxide nanoparticles. So the message that I'd like to give you from this slide is people, the ancient people, knew how to make nanoparticles for sure. But what they did not know was what was happening, and what they did not know was how to tailor them for different uses. That is something what we are trying to understand now for the last 30 or 40 years. But before going into some other issues, let me mention, which is not always mentioned in such kind of popular lectures, that size, of course, is a key factor in nanotechnology, but it is not only size. For example, I can have two structures with, say, the same dimension, maybe the same, the same diagonal and the same radius, but one is a cube and the other is some kind of a spheroid. Will they have the same properties? The answer is no. So shape through size also affect material properties. So you can have the same number of atoms drawn into a wire or a sheet or a blob. They will have different properties. Surface. We can have a nanostructure and we can decorate the surface or engineer the surface differently, and different surfaces will produce different effects. In addition to that, there's something called defects. Because what we see theoretically is something ideal, but almost all materials in reality, they have defects. So these defects inside a nanomaterial will also play a very, very significant role in determining their properties. So size, shape, surface, defects, and distribution play a very, very important role in determining properties of nanostructures. A little bit of terminology, which many of you may already know, that nanostructures can be of 3 different dimensions: a 2D, 1D, or 0D. Now, if we start from a bulk meaning that all the dimensions are large, they're not nanoscale, they're micron or more. Now, if I start squeezing the material in one direction, making it thinner, thin, very thin. So one of the dimensions is nanoscale, the other 2 are bulk. This and this is bulk, whereas this direction is nano. Such a structure is called a thin film or a nanosheet, where the atoms and the electrons inside are confined in this direction. When you squeeze it in 2 directions and one of the dimensions is bulk, we have a one-dimensional nanostructure, nanowire or nanorod. On the other hand, if we squeeze it in all 3 directions, then we have a nanodot. So we can have a 0D, which is a nanodot, 1D, nanowire, 2D, a thin film. In addition, you will learn as you take the course that it's very, very difficult to get a single nanostructure. They are so dramatically small. In most cases, what you have is a nanostructured bulk, a bulk material in which you have small nano inclusions. Either you deposit on a substrate, or you make a pelletized form of it, or you put it in a colloid, disperse in some solvent, or you embed in some matrix. So that is a nanostructured bulk material with nanoscale ingredients in it. Or we have nanocomposites, where you can have wires and 2D materials and dots all mixed up together to form a composite. Right? So these are the different forms in which nanomaterials, nanostructures can exist. About the synthetic approaches, how do we prepare nanomaterials? There are 2 broad approaches. One is called a top-down, and the other is called a bottom-up. In a top-down approach, it's simple. Basically, we have to start with a bulk material and then break it. It doesn't matter how you break it. Probably the ancient Romans or the Indians, they used simply maybe stone or a piece of iron to grind it. Today, we have mechanized mills where we can just, bang material, break it into smaller pieces. We can use lithography or etching processes. So a top-down process essentially means that you start with the bulk material, then you break it up into smaller and smaller components until you reach the nanoscale. The other process is bottom-up, where you actually start with atoms. Maybe you dissociate atoms in an electrolyte or in a solvent. And then you do reactions or just allow them to assemble to form tiny, tiny particles, tiny grains, and you don't allow this to grow on to form a bulk. So you restrict, you allow them to congregate to form tiny structures, and then you restrict. So there are many, many approaches of bottom-up, basically weight chemical synthesis, self-assembly, sol gel, where you start with individual atoms and allow them to congregate to form nanostructures. So these are the broad approaches of making nanomaterials, top-down or bottom-up. Okay. However, you will realize that working with nanostructures is not easy. There's a problem inherent in it. What is the problem? That nanostructures they're typically nanometer, that is 10 to the minus 9. Say 10 or 1 to 100 nanometer, roughly. But in order to see something, we need light, right? And light has a wavelength. The visible light, the wavelength varies from 400 to 800 nanometers, or 4,000 to 8,000 angstroms, from violet to red. So a nanostructure is much smaller compared to the wavelength of light. So using light, it is not possible to see a nanomaterial, because the maximum resolution of an optical microscope, a microscope that uses light, the theoretical resolution is 200 nanometers. So how do you see? Because it's like trying to locate a small grain of sand with the help of huge waves of a sea, waves in ocean. You cannot see a sand. The sand will be washed away. Similarly, nanostructures cannot be seen by light. So you need something whose wavelength is much smaller, comparable to the nanostructure, like X-rays or electron beams. So that is a challenge, because we are dealing with materials which we cannot see with light. We can see, we can form images in an indirect manner. So naturally the question comes, if we cannot see, how do we manipulate them? How we engineer them? How we will build machines out of them? Of course, we cannot do it with our hands. We cannot do it even with under a microscope. We need very, very special instruments to see and to manipulate nanostructures. So it's a technological challenge. Of course, when you have a large amount of them and you just use them to paint or you put them in steel, it's easy. But when you want to make devices out of these nanostructures, engines out of these nanostructures, gears out of these nanostructures, that's a formidable task, right? So the challenge of a nanotechnology course is to introduce you to this exciting world and this technology which will allow in manipulating nanostructures. A bit of physics in here. We know, or I guess you know, that if we consider one atom, then the energy levels in this atom are discrete. A single atom will always have a discrete energy level. But when you start bringing atoms together, then the discrete energy levels of the superposing atoms, of the outermost shells, the electronic energy levels, they split and combine. So when you have a large number of atoms in a bulk, then in addition to the discrete core energy levels, you get something called the energy band, which is a semi-continuum. So in a bulk material, you have energy bands in addition to the discrete energy levels. And in atoms, you have discrete energy levels. So what do we expect in a nanostructure? In a nanostructure, one key thing happens is that electronic energy structure is not like the bulk, is not like the atom, is somewhere intermediate. So the band structure changes. So a continuous band becomes discrete, and we get some effects which is called band gap widening, which has immense, immense application in many, many fields. And one of the major aspects of understanding what is happening in a nanomaterial is to understand how the band gap changes, how the electronic energy structure changes, and how they depend on size at the nanoscale. All right. Now, these are the things that the course will offer to you. But I will end by discussing some applications. But let me tell you that as students, you are living in a time which is very interesting, because till now, most of the cherished dreams of nanotechnology have not been realized. Meaning that we have not even seen the tip of the iceberg. A huge amount of things can be done, but we have done very, very little. This is because of many things. I think one of the major things is because it is interdisciplinary. It is not only a subject of either physics or chemistry or biology. We need a concerted effort of people coming from different disciplines, working together to make things happen. One of the amazing applications that we can have is, of course, in medicine and in pharmaceuticals. The reason is simple. If you look at all the biological components that play a very important role in our life, starting from water molecule to the coronavirus or the HIV virus, they're typically, their sizes are in the nanometer regime. So if a virus is in the nanometer regime, you need something in the nanometer regime to combat it. You cannot fight with an ant and you build an elephant. So you need something of that size. So nano or nanomaterials have very, very important applications in aspects of drug design, diagnostics, detection, targeting, drug delivery, to tissue engineering and therapeutics and implants, and many, many others. You know, one of the dreams of people working in the area of nanobiotechnology is to have a complete diagnostics come therapeutics in a single nanostructure. So the idea is simple, that you have a nanostructure, a nanoparticle, and you can functionalize this nanoparticle with elements of your choice. Something will go and bind to a diseased cell and give out light, so you know where the diseased cell is. There will be other component which can be initiated to release a drug. So you can load a drug, you can release a drug, you can detect. Many, many things can be done on a single nano platform. We are far from it because of many reasons. How do we direct? How they can be targeted? There are many, many aspects of that. So all the leading players in pharmaceuticals, they are investing a lot. So I believe experts who are trained today will play a very important role in the future times to build up structures which till now exists only in our dream. But there are things which are already realized. For example, orthopedic implants. Now, many of the orthopedic implants which are used or which will be used probably in future has some kind of bioactive nanomaterials or nanoporous structures, which make them more effective. Dental implants. I'm very proud of one of my students who has played a very important role in making some new generation dental implants with nanoscale surface engineering. And these dental implants are much better than the other variants of dental implants. So these are reality. But lab on a chip, going inside, doing diagnostics, therapeutics is still of a dream. Another application which I think has been undermined till now is in automobile. In an automobile, there are many, many parts. GM Safari has till now only used nanomaterials for the step assists. They use a particular kind of nanocomposite which makes it scratch resistant, lightweight, rust proof. Toyota, I know they used a kind of nano clay for making this belt, the timing belt cover of Toyota. Toyota also started making bumpers out of nanocomposites, which made them lighter and stronger and scratch resistant. But I am tempted to believe that many, many other parts of automobile industry will go the nano way in future. There are issues, there are technological challenges which has hindered that. So an engineer or a scientist getting trained today, I guess, will have immense scope in application in the automobile industry. Another area where the application of nano has been limited is construction industry. If any of you have been to Rome and witnessed this fantastic Jubilee church, which has a bright white hue, and that is because of titanium dioxide nanoparticles. These titanium dioxide nanoparticles were used for a binder to make them strong, but it also gives a very bright white color. So nanoparticles in construction materials can be used as binders. They can also be used for improving mechanical strength, mechanical durability. I know some of my colleagues working on carbon nanotubes impregnated cement. But again, these are more in the research area, not commercialized till now. But undoubtedly, the greatest promise in nanotechnology is in electronics. Many of you may have seen this graph before. This is the graph predicted by Moore, known as the famous Moore's law, which says it's a phenomenological law that the number of transistors in a chip has kind of doubled, goes on doubled every 6 years, every 18 months. So if you see the number of chips starting from 1970 to 2018, it's an amazing kind of fit with Moore's law. So the number of components, the size of the transistors have become smaller and smaller and smaller and smaller. So today, if you look inside a chip, it looks something like this, even with the most powerful microscopes. You won't be able to identify a single transistor or, the op-amp, nothing. It looks like a mesh. And none of these parts are made manually. They are all made through machines in clean rooms so that no dust particle comes in, and they are packaged and comes out in that manner. Now, a major problem here is that if you look at particularly these things, these coppery color, they have huge copper wires which connect the small parts. Now that imposes a restriction, because if you have a very long copper wire, you know that the joule heat generated will be very high, because the heat generated is proportional to the length and inversely proportional to the area. That's how the resistivity varies. And joule heat is I square RT. So, okay, even if you have forgotten that, this is the crux of the matter is if you make components smaller, then the heat generated becomes very high. So how do you solve that? Now, the modern electronic industry is faced with this problem. I don't know if you're aware that a laptop, almost 60 to 70% of its weight is dedicated to manage this heat. It's heat management, it's not electronics. Because a huge amount of heat is generated. So how to manage this heat? One prescription is to replace electrons by photons. And that can only be possible if we use nanostructures. That's a very exciting field in which I'm personally involved. Optoelectronics, photonics, and all the big players, TSMC, Taiwan Semiconductor Manufacturing Corporation, Samsung, Intel, IBM, they're all going this nano way. 9 years before, in 2013, TSMC became the first foundry to begin the 16 nanometer FinFET. In 2019, AMD officially launched the Ryzen 3000 series of CPUs, which are based on TSMC's 7 nanometer process. So these nanometer chips are already there. But most of these giants like Intel, TSMC, Samsung, IBM, all their technologies are completely patented. And there are expert nanotechnologists, scientists, engineers working there. And our idea is to train you so that you can jump into that bandwagon and make some kind of a breakthrough, which is needed. The whole world is crying for these breakthroughs, particularly in electronics. Okay, so that kind of brings us to the end of this delivery of lecture, but I would like to end with a very small quiz. We all know that a nanometer is 10 to the minus 9 meters. But I have a question that do we really understand how small is 10 to the power minus 9? If you look at internet, it will tell you that the human hair is 100 micron, which is like 100 micron, which is like 100,000 nanometers. So 1 nanometer is 100,000 times smaller than human hair. But how small is it? So when I came to New Orleans, I thought that, okay, instead of expressing the area of New Orleans, it is typically expressed in meter square or kilometer square. So the area of New Orleans is about 64,000 kilometers square. So what if I express it in nanometer square? That's easy, because a kilometer is 10 to the power 3 and a nanometer is 10 to the power minus 9. So the kilometer square would be how much? You can easily do that. It would be 10 to the 28 nanometer square. Okay. It's roughly 60 to 10 to the power 28 nanometers square, the area of New Orleans. Now say I want to buy out New Orleans, entire New Orleans. What do? I start buying land instead of kilometer by nanometer every day. And I value it at a very, nanometer is small, so I value it at a very small price, say 1 peso. 1 peso per 1 nanometer square. So I start collecting this 1 peso coins, one on top of the other. So how many pesos will I need? I will need 10 to the power 28 pesos, right? 60 to 10 to the power 28 pesos to buy out New Orleans. If every square nanometer is 1 peso, that's a small price, right? Now, if I start collecting coins and make a tower out of 10 to the power 28 peso, my question is, how high will this tower be of 10 to the power 28 1 peso coins? I don't know whether you are allowed to speak, but let's think. Will it cross, say, the highest mountain? Will it reach the moon? Will it reach the sun? If you do a quick calculation, assuming that a peso is about few millimeters, roughly, you can do that calculation, right? Few millimeters and put it, and then you'll see that this tower will be 10 to the 23 kilometers. That is 10 billion light years. And 10 billion light years is bigger than the size of our universe, the universe that we know. The Milky Way is only 10,000 light years. So this size is so amazingly large. What does it say? That a nanometer is so amazingly small. We talk of these numbers, but we don't understand what these numbers mean. That is what I wanted to convey. And with this, I welcome you all to the nano world. It was an introductory, a kind of something from here, something from there, the basic of what is nano. So I much appreciate questions from your end. Thank you very much.
Thank you, Dr. Ray, for this speech. It was very exciting to know more about nanostructures. Si alguien tiene alguna pregunta, por favor lo puede hacer abriendo el micrófono o en el chat. Con gusto aquí el doctor lo podrá contestar. ¿Alguien? Well, I think it was pretty clear. Juan Carlos, adelante.
Congratulations, Doctor. Excellent presentation. Very interesting. What do you think is the principal challenge of the nanotechnology in general? Or which is the principal limitation?
I think it was a little bit cut off. Juan Carlos, can you repeat the question, please?
Yes. What do you think is the main limitation of the nanotechnology in general?
You said the main limitation or the promise?
Yes.
The main
limitation.
That's a good question. I mean, the main limitation, there are many, but till now, I would classify it in two parts. One part is till now, we do not know the exact size-dependent behavior of most of the nanomaterials. The reason is that because we need to know both theoretically and apply it for experiments, then only we can handle it. For example, classically, when you are making machines and things like that, we know the science completely, Newton's laws. And at the same time, we have the technology to implement it. But at the nanoscale, the science that is operative there is quantum mechanics. And it is not easy to apply quantum mechanics to a large collection of atoms to get exact results. So the results that we get theoretically are on very ideal systems. But actual systems are not ideal. Actual systems, they have many defects, many problems. So till now, it's very difficult to exactly predict how a system will behave. We do not know that. That's the primary limitation. And of course, along with it is a technological limitation, that how do we manipulate such small structures? It's till now, we are unable to manipulate a single nanostructure. I can take a cup and move it from one point to other, it's bulk. But if I have a nanostructure, I can't even see it, even with a microscope. We need very special microscope. So how do I manipulate? How do I move it from one point? That's another challenge, a technological challenge. So we have a scientific challenge in terms of understanding, a technological talent in terms of dealing with it. We have another question in the chat.
Yes, was the change in the color of the solutions of different sized nanoparticles related to surface plasma resonance?
Yeah, it's due to surface plasmon resonance. I mean, plasmons, I don't know, whoever asked the question, it's a very good question, of course. And in these nanostructures, we get something called localized surface plasmon resonances. And the surface plasmon resonances can be tuned by tuning the dielectric, the refractive index, the relative refractive indices, and also the size and shape of the nanoparticles. This change in color is because of some kind of agglomeration. It cannot be completely attributed to size, but in an indirect way, it's related to size. That's a good question. It is related to surface plasma, of course, of the gold.
¿Alguna otra pregunta o comentario? Pues muchas gracias, doctor Rey, por tan maravillosa plática. Gracias a todos por su asistencia. En el Tecnológico de Monterrey estamos muy interesados en hacer este tipo y otros muchos tipos de investigaciones. Les vamos a hacer llegar por correo electrónico una oportunidad que tenemos dentro de la institución. Estamos ofreciendo una beca del 100% a todos aquellos alumnos que estén interesados en ingresar al Tecnológico de Monterrey en algún programa científico. Sabemos que México tiene una necesidad enorme por investigación y nosotros estamos buscando ese apoyo, tratando de encontrar esos talentos que México tanto necesita. Muchísimas gracias a todos. Voy a dejar aquí por el chat if you let me share your email, doctor. I will share it with everyone here. If you have any questions, you can send it directly to him. And I am also gonna leave mine in case that you have any questions or comments about these conferences or you need any information. Thank you very much and have a nice evening. Gracias, Dr. Rey.